So for section 4.7, we're going to look at simulating probability. And there's a couple ways of doing this. But whenever I'm simulating, basically what we're doing is we are using some procedure or process that behaves the same way as our true process, and our results should be similar. So this is a way that we can kind of approximate probabilities, and we can see kind of what we would see over multiple events. So for instance, rolling a die. I know the events. I know that our sample space has the numbers 1 through 6, right? So theoretically, the probability of getting a 3, right, there's 1/3 out of 6 in the sample space, would be 1/6, or I think that's 0.16 and rounds off to 7. So the probability of getting an even number, theoretically, there are, let's see, 1, 2, 3 even numbers. So 3 out of 6, which would be 1/2 or 0.5 or 50%. So this is what we would expect in theory. But what happens in actual practice, right? If I were to roll a die, does that mean that a 3 will occur every 1 out of every 6 times? Well, in theory it should, but the idea is that in reality there's going to be some deviation from that. Sometimes it occurs more, sometimes it occurs less. Okay? So what we're going to do is we're going to compare this theoretical probability to an actual probability we get through a simulation. So if I wanted to simulate rolling a die, and there are little apps that I could do and just, click a button and roll a die, but basically we could actually roll a die. So actually roll a die, so use a real die, and just roll it to simulate rolling a die, right? But I could also use a table of random digits. And so what I did is here I pulled the list of numbers that I've gotten out of a book of table of random digits. This always weirds people out because they're like, there are books with tables of random digits? Yes. This is what we used to do is before we had technology to generate random digits, we would have books full of random digits. And for it to be a random digit table, each number would need to have an equal chance of showing up each time. And so then each trial would be independent. So just because there's an 8 here doesn't mean there won't be another 8. There could be, sometimes we get numbers that repeat. So the idea is that when we try to come up with random digits in our mind, we tend to be biased. And I heard a really good story about a professor that's way smarter than I am, but basically was able to look at tables and he could tell whether they had been randomized or made up. And he would challenge his class and say, here's what I'm going to do. I'm going to have one of you flip this book open and copy down 20 numbers. And then I'm going to have, 5 of you that are just going to write 20 numbers that you think are random. And then he would leave the room and have them do that and come back in, and he could flip through each one and go real, fake, 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 real, and just could lay it out. He could see, because in actual random digits, we see things that we wouldn't expect, like numbers together or numbers repeating. There are freaking 3 9s in these 10 numbers. We wouldn't think to do that randomly, okay? We can also use technology to do this, and I'll show you that. With our calculator, we will use random integer is the command. We'll have a minimum, a maximum, and then how many we want to generate. Okay, so I'm going to go ahead and use this table first, and then we'll use technology, and we'll kind of show how we could simulate. Actually, I'll start with the dice up here, okay? So let's do the probability of getting a 3. Okay, now we know in theory it should be 1 out of 6, but here are 10 numbers. What numbers can I use to represent, right, rolling a die? Well, I need each number to have a 1 out of 6 probability. So here's where we say, well, maybe we only use the numbers 1 through 6. I could also use the numbers 0 through 5. But the idea is that there needs to be 6 numbers that represent rolling a die. So I'm going to go ahead and keep the 1 through 6. That's pretty simple. But that means any number that's not a 1 through 6 we can't use from our table. So then I look at this table and I go, okay, so what's the probability of getting a 3 here? Well, we have 1 3 out of 1, 2, 3, 4. 3 out of 4, or 0.75. Now this is what we call an experimental probability. We got this from running an experiment. That is not the same as 1/6. But the idea is, if I continued through this book and I continued through the list, I would expect this probability to get closer and closer to the actual theoretical probability. And this is where we'll lead when we're going to run tests on probability, because if I did this over and over and over again and the experimental probability doesn't get closer to the theoretical probability, then we say, well, maybe the theoretical probability isn't true. Or maybe we have a loaded die. Or so those are the types of things that we can do. I can do the probability of an even here. So once again, I'm just going to use the numbers 1 through 6. Looks like I have 3 evens out of 4. Oh, that last one was wrong. I hope you're screaming at your screen. There was 1 3 out of 4 G's, which is 0.25, which is still different than the theoretical probability, but not as extreme. Sorry about that. So there was 1 3 out of the 4. If I do the probability of even, there are 3 evens out of 4. That would be 0.75. That's the experimental probability, okay? I can do this with my calculator as well. So if I do random integer 1, 6, and we'll generate 10 numbers, okay? And if you do this, you probably will get different numbers than me, and that's okay. Let's go to menu, probability, random, and there's going to be integer. You can also type in the name. I'll do that again. Menu, probability, random, integer. I need a minimum. If I'm rolling a die, we go from 1 to 6, and we're generating 10 numbers. Now this time I don't have to throw anything out because I told it to only give me numbers between 1 and 6. So what is our experimental probability on this list of getting a 3? Well, I see 2 3s out of the 10. So this would be 2 out of 10, or 0.2. That's for getting a 3. If I did even, remember this should be 50% in theory. Well, there are 1, 2, 3, 4, 5. Awesome. So that would be 5 out of 10, or 0.5 for an even. But the idea is, if we did this over and over and over again, and I can keep hitting enter, just to give you a couple examples, it's not always going to be 50%. How many evens do we have here? 1, 2, 3, 4, 5. All right, they're going to make a liar out of me. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7. Freaking 8 evens, right? So the idea is, in theory, it should be that, but when I do random digits, you can get actually what? 8 evens out of 10. Just like later on, if I kept doing this, I might get 2 evens out of 10. The idea is it will balance out over time. So the experimental probability, we get it basically jumping a lot more up and down around the truth, but over time it should approach the truth. All right, so the probability of having a child that is male or female theoretically should be 1 out of 2, 1 out of 2, right? If I use the tables and I want to use 0 through 9, so I'm going to use those 10 digits again, okay? So let me scoot this down. And then we could say, well, I need it to what numbers would I choose to give me a 50% chance? Well, I could have 0 through 4 and 5 through 9. That would be 5 numbers and 5 numbers. So using those numbers, 0 through 4 would give me 1, 2, 3, 4 boys. And make sure I did that right. 1, 2, 3, 4, 5, 6 girls. We could also just split it up as like even and odd. You'd have to count 0 as even, which I don't want to get into that argument, but basically all the evens and zeros. So if I did that, that would be even, 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 even. So that is exactly 5, right? So that would be 5 out of 10 and 5 out of 10. So depending on how you set it up, you may get different results, but that's how I would use that table. Now, if we wanted to simulate having 152 babies, oh my goodness gracious, right? I'm going to do this using technology. So I don't want to have to look through 152 numbers and try to count evens and odds. I'm going to choose simple numbers. Yes, I can do 0 through 9, but I could also just do 1 and 2. 1 is male, 2 is female. I would argue there's even an easier way of doing this. 0 is male, 1 is female. This is going to be the way that I'm going to choose to do this, where 0 is male and 1 is female, because then I can have the calculator count how many females there are very quickly, okay? So to do this, we're going to use the command random integer. I only need to generate 2 numbers because I need a 50-50 chance. So I can have it go from 0 to 1 and generate 152 babies. So let's just start with that. Random integer, menu, probability, random, integer, 0, 1, 152 freaking babies. How many girls are there? How many ones are there? I don't really feel like counting through all of those. So what I can actually do is I can just tell it to sum or to add up everything from this list. Well, what did it do? Well, since the guys were 0 and the girls were 1, it added up all the ones. How many females did we have? 70 females, which means the other 82 would be males. Is that exactly 50-50? No. But if we did this over and over and over again, then our experimental probability, I got a 152, our experimental probability basically gets closer and closer to the theoretical. And if it doesn't, then one of these is wrong. One of these has an issue. Either there's a bias in our experiment, or the theoretical maybe isn't the truth. Okay? Last example. This is something near and dear to my heart because, and I've told many of you before that I spent about 11 years teaching in high school. And when I did that, I had a friend that ended up being right in the room next door to me. And one day it was my birthday and I was all happy and I went up and said, "Hey, today's a wonderful day." And she goes, "Yeah, it is." And I said, "Well, why is it a wonderful day for you?" And she goes, "It's my birthday." And I said, "You're kidding. It's my birthday. And we've been working together for years." And so I thought, this is my birthday buddy. Like literally, I still go on Facebook every year and I say, "Happy birthday, birthday buddy," right? This is my special thing. Then statistics came and ruined it all for me because we said, okay, well, we have about 100 employees, 100 staff at this school, okay? What's the probability of people sharing a birthday? Well, in theory, there's 365 days in the year. So the probability, well, we could say is 1 out of 365. But this is a much harder question. We're saying, what if there were 100 people? How many of them would share a birthday with somebody, right? Was this big magic special occasion? Well, let's see. So we could simulate 100 people. So we could do random, integer. I want to generate a number between 1 and 365. Those would be the days of the year, right? And I'm going to do this for 100 numbers. I'm going to go ahead and do this on a list this time, okay? So I'm going to go back to my calculator, and in a spreadsheet, right here, I'm going to go up to the equal sign and do statistics, no data, random, there it is, integer. I can also just type it in. I'm generating days from 1 to 365, and we are doing 100 because there's about 100 teachers at the school I was at. Ta-da! Well, it's hard to compare. Are there any other 51s, any other 57s? So what we could do is we could organize this, which we've done before. So go up to the top, menu. I believe it is under data. Is there a sort? Oh, it's under actions. Actions, sort, ascending. So now they're all in order. This is somebody that was born, what, January 1st, January 3rd, January 13th. If I go past, this is January 31st. This represents February, what would that be, the 2nd, right? Because January ends on the 31st, so February 2nd. So there's my sister's birthday right there. So what we want to do is we want to say how many people share a birthday. Well, 1, 3, 6, 8, 13, not looking good. 14, 18, 19, 22. Bingo. Ding, ding, ding. Here's me and my buddy, right? That's 2 people so far. Let's keep going. 27. Another 2 people. So now we have 4 people that share a birthday out of these 100. Let's keep going. 5, 6 people that have a birthday buddy, right? Keep going. 8 people. I'm lost count. Thinking about too many things. Give me a second. There's our first ones right there. So right here is 2. Maybe I should make a tally as we go. So 1, 2. 3, 4. 5, 6. 7, 8. 9, 10. 11, 12. 13, 14. 15, 16. 'Let's see. What are we on? 17, 18? 19, 20, 21. Wait a second. 3 people, right? That's going to happen. There were 3 people. So these people had like 2 birthday buddies at the school. So that's another. I think I might have did that wrong. Give me a second. 3, 4, 5. 1, 2, 3, 4. There we go. So that's 1 that's left there. So right now I'm at 21. Oh my freaking goodness, right? It's like, you think that would happen? 3 people that are born basically, what is that, December 30th, right? So 3 more at the end. 1, 2, 3. So here we have 5, 10, 15, 20. We just figured out 24 people shared a birthday out of the 100. So here I thought, oh my gosh, this is a once in a lifetime ordeal. But basically, our theoretical probability for this is kind of hard to calculate. We will actually learn how to do that in the next chapter, to calculate this probability exactly. But if a probability is hard to calculate, then what we can do is we can use simulation to figure out what would the probability be. Well, we said about 24%. So if I continued to work at a school with 100 people, 1 out of every 4 jobs that I got, I would expect to share a birthday with somebody. There's about a 24% chance, based on our simulation here, that I shared a birthday with somebody. So, like I said, still not super likely, but it kind of, took the magic away. So, sorry about that if you had a birthday buddy and I just ruined it for you too. But, probability. What are you going to do? The only other thing I wanted to do just at the end of the notes is just kind of go through a couple things just to make sure that you have this vocabulary. That a certain event occurs, A with a line over it. That is not the mean of A. That's the probability of it not occurring. Or, I'm sorry, that's stating that the event does not occur. When I add the P in front of it, that's saying the probability of event A occurring. This is the probability of it not occurring. The word for that is complement, okay? Not compliment, we're not saying something nice, complement to complete. Here's some formulas for that. Basically, the probability of A not happening is 1 minus the probability of A happening. It also means the probability of A happening is 1 minus the probability of A not happening. Or if I add those two probabilities, they should add to 1. We also have, with multiple events, dependent and independent probabilities. Sorry, right there. And so when we have multiple events, the and we get by multiplying. That will either occur by taking the probabilities and multiplying them, or if it's dependent, A times the probability of B given A. So we have a whole other section on this, but just make sure that you have these formulas for the test. Or always means the same thing. We basically are going to add and subtract any potential overlap. So this formula works for both independent and dependent. What changes is this and. The and is different depending on whether it's independent or dependent. So, and then one other way of thinking about it, if it is independent, probability of B given A is just the probability of B. These basically should be the same because A has no effect on B. It's independent. Okay? If it's independent, the probability of A and B would just be the probability of A times the probability of B over the probability of A. What happens? I'm just left with the probability of B. Basically, A has no effect on B. Versus over here, the A and B, we're going to get, I encouraged you to use counts to do that, but this idea of given that, it's on your quiz. I don't go too crazy with this, but just expect that on the test.